A rock crusher is most appropriately classified as varying duty. While it could also be considered as intermittent duty case 1, the varying size and density of the rocks make it difficult to predict the load conditions with any certainty. Therefore, classifying it as varying duty acknowledges that the load and duration of operation can vary significantly. This classification aligns with the definition of varying duty in National Electrical Code or NEC Article 100. To further elaborate on motor duty classifications as they pertain to applications like rock crushers, let's delve into the specifics outlined in Article 100 and related sections of the NEC, particularly Table 430.22e. This table necessitates accommodations for motors operating under specific conditions. It's essential to clarify the definitions of the duty types and how they relate to real-world applications. Firstly, continuous duty refers to operation at a substantially constant load for an indefinitely long time. This is straightforward and applies to motors that run continuously without significant variation in load. Secondly, intermittent duty involves operation for alternate intervals of 1. Load and no load, 2. Load and rest, or 3. Load, no load, and rest. Now let's dissect these intermittent duty scenarios. Case 1, load and no load, implies the motor is constantly running, but the load it drives alternates between being loaded and unloaded. An example might be a conveyor system that sometimes carries material and sometimes runs empty. The key here is that the motor doesn't stop, so there's no repeated starting current issue, except for the initial startup. Case 2, load and rest, means the motor runs with the load, then stops completely. This involves repeated starting under load, which can lead to extreme starting currents. Think of a pump that fills the tank and then shuts off until the tank needs refilling. Case 3, load, no load, and rest is a combination of the previous two. The motor runs under load, then runs without load, and finally stops. In this case, the starting current is repeated, but it may not be as extreme as in case 2 because the motor restarts without a load. A complex machine cycle might exhibit this behavior. The ambiguity arises because there's no specified time frame for these events. The NEC doesn't dictate how often these load changes must occur for the duty to be classified as intermittent. Thirdly, periodic duty is intermittent operation where the load conditions are regularly recurrent. This is essentially intermittent duty with a periodic time frame. However, the NEC doesn't define what constitutes a periodic time frame. Is it every 30 seconds, every 5 minutes, or every hour? The lack of a specific time interval can make this classification challenging in practice. Fourthly, short-time duty is operation at a substantially constant load for a short, indefinite, specified time. Again, the NEC doesn't specify what that time should be. It could be 10 seconds, 30 seconds, or 5 minutes. The critical aspect is that the duration is both short and well defined. Finally, varying duty involves operation at loads and for intervals of time, both of which may be subject to wide variation. This classification doesn't mention rest, implying the motor is always on. The wide variation refers to both the magnitude of the load and the duration of each load. A motor subjected to light to extreme loads for short to long periods would fall under this category. Now, applying these definitions to the rock crusher, it's clear why varying duty is the most appropriate classification. While it might seem to fit intermittent duty case 1, alternate intervals of load and no load, the unpredictable nature of the rock crusher's load makes varying duty a better fit. The size and density of the rocks being crushed are rarely consistent. This means the motor experiences a wide range of loads, and the duration of each load varies significantly. It's difficult to predict these load conditions with any certainty. Therefore, classifying the rock crusher as varying duty acknowledges the unpredictable nature of its operation. This aligns directly with the NEC Article 100 definition operation at loads and for intervals of time, both of which may be subject to wide variation. It would be difficult to classify the rock crusher as periodic because there's no way to ensure the load is truly periodic. The inconsistency in rock density means the loading will be inconsistent even if the rock is fed at a constant rate. Consider the implications of misclassifying the motor duty. If you were to underestimate the demands on the motor, you might select a motor that's too small or doesn't have adequate thermal protection. This could lead to premature motor failure, downtime, and increased maintenance costs. On the other hand, overestimating the duty could lead to selecting a motor that's larger and more expensive than necessary. This increases the initial cost of the system and can reduce its overall efficiency. In selecting the appropriate motor for a rock crusher, several factors must be considered in addition to the duty cycle. These include the horsepower rating, the service factor, the insulation class, and the ambient temperature. The horsepower rating must be sufficient to handle the peak loads experienced by the crusher. The service factor is a measure of the motor's ability to handle overloads. A higher service factor indicates a greater ability to handle temporary overloads without overheating. The insulation class determines the maximum operating temperature of the motor. The ambient temperature is the temperature of the surrounding environment. Motors operating in high ambient temperatures must be derated to prevent overheating. Let's consider some specific examples. A small rock crusher used in a laboratory setting might experience relatively consistent loads. In this case, intermittent duty case 1 might be appropriate. However, a large industrial rock crusher processing a variety of rock types would almost certainly be classified as varying duty. It's also important to consider the control system for the motor. A properly designed control system can help to reduce the stress in the motor and extend its lifespan. For example, a soft starter can reduce the starting current, while a variable frequency drive or volts FD can allow the motor speed to be adjusted to match the load requirements. This can improve the efficiency of the system and reduce wear and tear on the motor. Now let's discuss some of the relevant NEC sections that provide guidance on motor protection and control. Article 430 covers motors, motor circuits, and controllers. Section 430.22 provides requirements for motor circuit conductors. The size of the conductors must be based on the motor's full load current and the duty cycle. For varying duty motors, the conductors must be sized to handle the highest expected load. Section 430.32 covers motor overload protection. Overload protection is designed to protect the motor from overheating due to excessive current. The overload protection device must be sized appropriately for the motor's full load current and the service factor. Section 430.52 covers motor short circuit and ground fault protection. This protection is designed to protect the motor and the circuit conductors from damage due to short circuits or ground faults. The short circuit and ground fault protection device must be sized to allow the motor to start without tripping, but must also provide adequate protection in the event of a fault. In addition to the NEC requirements, there are also industry standards that provide guidance on motor selection and application. The National Electrical Manufacturers Association or NEMA publishes standards for motor dimensions, performance, and testing. These standards can be helpful in selecting a motor that is suitable for a particular application. Let's recap. When classifying motor duty for a rock crusher, varying duty is generally the most appropriate classification because the load and duration of operation are subject to wide variation due to the inconsistent size and density of the rocks being crushed. Understanding the different motor duty classifications and the relevant NEC requirements is crucial for ensuring the safe and reliable operation of motor-driven equipment. Consider a scenario where a rock crusher is initially classified as intermittent duty case 1 load and no load. The electrical engineer sizes the motor circuit conductors and overload protection based on the assumption that the motor will experience relatively consistent load cycles. However, after the crusher is put into operation, it becomes clear that the load varies significantly due to the inconsistent size and density of the rocks. The motor frequently experiences overloads, and the overload protection device trips frequently. This results in downtime and lost production. To correct the problem, the electrical engineer must re-evaluate the motor duty classification and resize the motor circuit conductors and overload protection accordingly. This involves additional cost and effort. This scenario highlights the importance of accurately assessing the motor duty cycle and selecting the appropriate motor and protection devices. A thorough understanding of the application and the potential variations in load is essential for ensuring the long-term reliability and performance of the motor-driven equipment. Let's further illustrate with a comparative example. Imagine two scenarios. Firstly, a conveyor belt carrying uniformly sized boxes in a warehouse, and secondly, the rock crusher. The conveyor belt, assuming a consistent feed of boxes, operates under a relatively constant load. While it might experience brief periods of no load if the feed stops, the load variations are minimal and predictable. Therefore, this application could be classified as continuous duty or, at worst, intermittent duty case 1. Now, consider the rock crusher. The rocks fed into the crusher vary in size, density, and hardness. The motor's load fluctuates dramatically as it crushes larger, harder rocks versus smaller, softer ones. The duration of these load peaks is also unpredictable. This significant and unpredictable variation in load makes varying duty the most appropriate classification. It's also important to differentiate between varying duty and periodic duty. While the rock crusher might experience some cyclical patterns in its operation, such as a consistent feed rate of rocks, the variability in the rock properties prevents it from being classified as periodic. Periodic duty requires regularly recurrent load conditions, which are not present in the rock crusher application. Consider the implications for motor control. With varying duty applications like the rock crusher, sophisticated motor control strategies can improve performance and efficiency. For example, a volts FD can adjust the motor speed based on the real-time load requirement. This allows the motor to operate at its optimal efficiency point, reducing energy consumption and heat generation. In contrast, a motor driving a continuous duty load might not require such advanced control strategies. A simple on-off control might be sufficient. Proper documentation is also crucial. The motor duty classification and the basis for that classification should be clearly documented in the project specifications and drawings. This ensures that everyone involved in the project, from the electrical engineer to the maintenance personnel, understands the motor's operating conditions and the required protection and control measures. This documentation should also include details about the expected load variations and the measures taken to mitigate the impact of those variations on the motor. In summary, classifying a rock crusher's motor duty cycle is not just a theoretical exercise. It's a critical step in ensuring the safe, reliable, and efficient operation of the equipment. By carefully considering the load characteristics and applying the relevant NEC definitions, engineers can select the appropriate motor and protection devices, minimizing downtime and maximizing productivity. The key takeaway is that varying duty is the most suitable classification for a rock crusher due to the unpredictable nature of the rock load and the wide variation in both the magnitude and duration of the loads experienced by the motor. Understanding the nuances of motor duty classifications and their practical implications is essential for all electrical engineers and technicians involved in the design, installation, and maintenance of motor-driven equipment. This knowledge helps to ensure that motors are properly selected, protected, and controlled, leading to increased reliability, reduced downtime, and improved overall system performance. Consider the impact of technological advancements on motor duty classifications. As sensors and control systems become more sophisticated, it may be possible to more accurately predict and manage the load variations in applications like rock crushers. This could potentially lead to the development of new motor duty classifications or refinements to the existing ones. For example, a smart control system that uses real-time data to adjust the motor speed and torque could potentially allow a rock crusher to be classified as a more specific type of intermittent duty, rather than the broad category of varying duty. This could enable engineers to optimize motor selection and protection, further improving system performance and efficiency. However, even with advanced control systems, the inherent variability in the rock properties will likely continue to make varying duty the most appropriate classification for many rock crusher applications. The key is to carefully evaluate the specific application and select the motor duty classification that best reflects the actual operating conditions. In conclusion, the classification of motor duty is a critical aspect of electrical engineering design and should not be overlooked. While the NEC provides definitions for various duty types, the interpretation and application of these definitions require careful consideration of the specific application and its load characteristics. For rock crushers, varying duty is generally the most appropriate classification due to the unpredictable nature of the rock load. By understanding the nuances of motor duty classifications and applying them correctly, engineers can ensure the safe, reliable, and efficient operation of motor-driven equipment. Remember to always consult the latest edition of the NEC and other relevant industry standards for the most up-to-date information and guidance.